Hello and welcome to our ECE 499 project presentation. Accurately and frequently monitoring the vital signs of a patient in a clinical setting is critically important to ensure proper care for the patient. In an acute clinical setting, such as a post-operative environment, vital signs are measured for each patient as frequently as every 4 hours. Providing healthcare workers with an efficient, inexpensive, and hassle-free system for measuring some vital signs would ensure that they are measured frequently and accurately. In the wake of the current COVID-19 pandemic, it has become important to reduce the amount of direct physical contact between healthcare professionals and patients. Measuring patient vital signs in a contactless way would directly reduce the risk of hospital-related infection transmission. This technology would benefit both the healthcare workers and the patients in the clinical or hospital setting. Our project aims to develop a wireless system which measures heart and respiration rate. The data collected is also used to compute an important vital sign metric, the heart rate variability, or HRV. Heart rate variability is the measure of the variation in time between heartbeats. It is computed using data from multiple heartbeats over a set period of time. The standard for heart rate variability measurements is to use either 24 hours or 5 minutes worth of data. Heart rate variability has been shown to be an important predictor in deterioration in cardiac patients. Modified HRV has been associated with a range of clinical outcomes, including increased mortality following myocardial infarction. It has been shown to be a significant feature for machine learning models in classifying or predicting dangerous heart abnormalities. Heart rate variability is really a catch-all term which refers to a variety of aspects in the variation in your heartbeats. For our project, 3 metrics were chosen to give a more robust picture of the true HRV value: the RMSSD, the SDNN, and the HTI. SDNN refers to the standard deviation of NN intervals, or the time between heartbeats. RMSSD is the root mean square of successive differences, which is computed by the quadratic mean of the difference in time between adjacent heartbeats. HTI refers to the heart rate variability triangular index, which is the total number of NN intervals divided by the height of an NN interval histogram with bins of approximately 8 milliseconds. Together, these parameters provide a robust estimate of the overall heart rate variability. The goal of our project was to design and develop a prototype system to measure respiratory rate, heart rate, and heart rate variability metrics. The system is wireless so that healthcare professionals using the system can monitor patient vital signs while maintaining a safe distance. The project focuses on obtaining heart rate variability metrics due to their application in machine learning paradigms, which can aid healthcare workers in patient diagnosis. The wireless respiratory and heart rate sensor system consists of a hardware and a software component. The IWR 1443 mmWave evaluation board from Texas Instruments is used as the hardware component to sense and process respiratory and heartbeat signals. Millimeter waves, aptly named for their wavelengths between 1 and 10 millimeters, are used by the evaluation board in a radar system. The reflections of high-frequency pulses are sampled, and through analyzing the phase difference of consecutive samples, a highly sensitive displacement measurement can be made. Sample data is processed by firmware on the board, with a respiratory and heartbeat waveform being extracted through bandpass filtering. The firmware also processes the heartbeat waveform to obtain the time indices of the heartbeat peaks. This data is then passed in packets over a UART connection to software in order to calculate the heart rate variability metrics and to display breathing and heart rate data. Heartbeat data is collected over a 5-minute interval by the sensor before HRV metrics are calculated. A 5-minute interval was chosen over the standard 24 hours so that the HRV metrics could be obtained more frequently for a fast patient diagnosis in a healthcare setting. The hardware module collects the time indices of the peak heartbeats over the 5-minute interval and then passes this data to a MATLAB program where the indices are converted into time between heartbeats, which is needed to calculate each HRV metric. A MATLAB GUI was designed to provide the user with a graphical display of collected respiratory and heartbeat data, as well as a means of starting and stopping data collection. A start button is provided to begin the data collection over a 5-minute interval. A timer will count down and display the time remaining in this collection interval. Breathing and heart waveforms will be updated in real time as data is collected, and with the breathing and heart rate values displayed. When the 5-minute interval has expired, the HRV metrics will be calculated and displayed. At any point, the user can press the reset button to stop data collection. Here you see a typical state diagram for the system. The user begins by pressing the start button of the GUI, sending a start command over UART to the hardware module. The hardware module begins by mmWave pulses or chirps and sampling the reflected signals. The signal is then processed by FFT and binned to determine the range of the patient. From the spectrum of the corresponding range bin, phase information is extracted and displacement measures determined through analyzing the phase difference in the spectrum of the reflected signal. 2 bandpass filters are then used to filter the signal into separate breathing and heart rate waveforms. Both waveforms are analyzed in the frequency domain rate estimate determined through selecting the maximum frequency value. The heartbeat time domain signal is also processed to extract the time indices of the heartbeat peaks. Data is then sent in a packet back to the software module where breathing and heart plots and rate estimates are updated in real time on the GUI. When the 5-minute interval has expired, the software module uses the buffer of heartbeat peak indices to calculate and display the HRV metrics. A complete test plan with unit, system, and performance tests was created for validation of all aspects of the design. Unit tests cover the individual components of the GUI used to display data to the user, as well as the firmware collecting data on the evaluation board. System tests ensure that the data collected from the hardware is properly processed and sent to the user. Finally, performance testing validates that the vital sign results are accurate and comparable to existing vital sign measurement technologies. The results of preliminary performance testing are promising, showing that the collected heart and respiration rates are accurate to within 10% of their actual values. The computed HRV values conform with expected values from the literature. Frequently and efficiently measuring patient vital signs has always been critical to patient care. It has never been more important to minimize unnecessary contact between healthcare workers and patients. The proposed wireless vital signs measurement system provides healthcare professionals with a feasible method of maintaining accuracy in their monitoring system while reducing direct contact with their patients. The added heart rate variability metric provides more insightful data relevant to healthcare professionals and data scientists alike.